Professor Vinod Kumar.
Yeah, I missed my video connection. However, anyway, it is a great moment for IAPT as well as RC-07 to. Can you hear?
Yes,
Yeah.
sir.
Yes,
Yeah,
yes, yes.
my video I
Sir,
got lost. I will try to connect again.
Sir, just a minute. I'm just
Hmm.
trying to live stream. Just give me a minute.
Okay.
Yeah. You can start now. Yeah. Sir, you can
Yeah.
start.
Yeah, it is a great moment and pride moment for RC-07 to host this, unique activity. It was, in fact, a phone call from President of IAPT, Professor Ahluwalia sir, to Joshipura sir, and then that is how it got worked out. And it is a right time that IAPT, as a physicist fraternity, should think about how it can be discussed in a wider perspective to reach to the students as well as the teachers the importance of quantum science and technology. We are actually in the midst of this quantum revolution, second quantum revolution, and it is hopeful that many new technologies are on the way, so that we may have to equip our next generation to cope up with such situations. This I welcome. It is a bright moment for us to welcome all the dignitaries, particularly Professor Ajay Ghatak, who is the first speaker of today's this event, the series of 3 days event, and Professor Joshipura, professor and an enthusiast for the physics popularization and ideas around. I welcome Professor Ahluwalia sir, President of IAPT, Professor Regaben, Secretary of IAPT, Pratul Desai, our Secretary, RC-07, and all others who have joined for hearing and encouraging this event. With this, I giving back my mic to Pratul.
Okay, so I will request now Professor Rekhaben Ghorpade to say a few words.
Thank you, Professor Desai. Respected speaker, Professor Ajay.
Everyone may switch off the mute.
Yeah.
Everyone.
Please mute yourself, except the one who is talking. Okay. I think we should proceed now. Respected speaker, Professor Ajay Ghatak, President IPT, Professor Ahluwalia ji, Professor K. Joshipura ji, our former General Secretary and a very, very active person, not only in RC-07, but the entire IAPT. All the office bearers of RC-07, Professor Vinod Kumar, PC Vinod Kumar, Professor Pratul Desai, Professor Punit Sutar, and everyone here, and all the wonderful participants. Very warm welcome on behalf of Indian Association of Physics Teachers and the RC-07. I'm extremely happy and feel proud to be with you all today to have this kind of a program. As this year 2025, we are celebrating as an international year of quantum science and technology. And we are happy, and I congratulate RC-07 Gujrat for taking the initiative in having a program which is a curtain raiser program. And then the program will be held and organized all throughout the country throughout the year. So with this, we are going to have Professor Ajay Ghatak as a speaker to start with. And I think this is a very proud moment for all of us to have him, because all of us who are here have used his books on quantum mechanics and optics. I think we have grown and we have learned physics through his books, and it's really a very great time or great moment to meet Ajay Ghatak every time. So welcome, sir, on this platform. Now, for IAPT members, IAPT activities are known to them. But there are some people who have joined here in the participants list, I can see, who are not the members but would like to know about the IAPT. And for them, let me tell you that IAPT is now 40 years old organization, which was established in 1984 by Professor Khandelwal and like-minded people like Professor Babulal Saraf, Professor Virk, Professor H.S. Hans, and there were so many. Because I mean, all the information will be available on our website also. Some of the flagship activities which I would like to mention, which IAPT conducts, is one of the very important activity that IAPT has is the national standard examinations, which is the first step towards the international Olympiads. And this is the only examination which allows to students or gateway to the international Olympiads. So a very important thing. And we also conduct the NGP National Graduate Physics exams for UG students. IAPT also conducts many competitions like competition, a national competition in innovative experiments in physics, then competition in computational physics, essay writing in physics. Then we have also introduced the photo essay competition. Now IIPT also conducts the international, IYPT, that is the national, actually NYPT, which is very similar to IYPT, that is international, sorry, physics tournament, I mean, young physics tournaments. This is a very unique competition that we have introduced here. I suppose someone is, using a cursor and whiteboard here. So I think please refrain yourself in abusing the platform. Let me continue. So these all competitions which are conducted at national level by IAPT are the competitions which give a wider platform and allow the participants, the students as well as teachers, to explore themselves at the national level. And we have also started the exemplar RC awards for the those who are doing for the regional councils who are doing exemplary work at their regional levels. And this is not the competition among the RCs, but this is we are incentivizing these RCs because we are giving them the cash prizes. And of course, it's a motivation to the regional councils. So IPT, I forgot to tell you that IPT has 24 regional councils and around 7 sub-regional councils, through which we are trying to reach out to unreach every corner of the country. And our programs, which is we are trying to achieve our objective by having organizing programs through the regional councils and the RC levels. We also have a national Anveshika network of India, NANI, which is a coordinator at present is Professor Verma, HC Verma. And we have around 27 Anveshikas all across the country, through which we are giving, they are really working on innovations and also inculcating the culture of experimentation and learning by the experiential learning. So there are several things which I can go on, but I don't want to come in between the today's speaker, Professor Ghatak, because I know everyone here in the online meeting, is eager to hear Professor Ajay Ghatak. And those who are interested in knowing much more and becoming a member, I request them to kindly visit our website, indapt.org.in. And every information will be available on the website, how to become member and what are the activities. We also have a monthly bulletin which is published every month, and this is sent to the every member who, earlier we were sending everybody a hard copy, but now we have slowly decided to cut down the number of hard copies, and we have started sending the bulletin by email, so that we are cutting down on the cost of the hard copy. With this, let me welcome once again Professor Ajay Ghatak and everyone in this online meeting. And the platform is yours. So over to Pruthul Desai, sir.
Thank you, Rekha ma'am. Now I would request our president, IAPT president, Professor Ahluwalia, who this entire program is his brainchild. So I would like to him to give
Yes.
a information about the program and the activity that we are planning to carry out throughout the year. Professor
Thank you very
Ahluwalia.
much.
Thank you. Thank you very much. Welcome to this very special program of IAPT to all the members and our honorable speakers, Professor Ajay Kumar Ghatak and Professor K.N. Joshipuraji. I think it's a very special occasion because 2025 is the year when we are celebrating the beginning of the proper quantum mechanics. Before that, quantum mechanics was semi-classical kind of a thing. What we have in IAPT, this program, is this that we are going to conduct every month this program for 3 days, in which we will have 5 to 6 speakers, and we will try to carry forward the kind of mission which has been enshrined in the United Nations resolution on this particular event itself. And I think everybody is talking about quantum mechanics in very many manifestations, particularly the evolution of quantum computer, which is something which is going on, the kind of work opportunities which will be available because of the quantum computing and quantum missions which are happening in almost all the countries. We also thought that we should really not miss this chance to bring awareness not only to physics community, but outside the physics community also. These lectures will be available on the YouTube channel of IAPT. So that means those who are not able to join at this moment, they will be able to join as and when they find time and watch these wonderful presentations. One thing more I would like to mention, if I get a permission from Professor Ghatak, that I think it is the 50 years of this publication of Professor Ghatak's book of quantum mechanics. And I think this is a great, great time to rejoice that his book became so popular. And whenever you talk to anybody, he will say, yeah, we have read that book. That was the book. And one of the very characteristic feature of that book was that there was a lot of emphasis on problems in quantum mechanics and their solutions. I think that was for the first time that a good book on the Indian scene came. Otherwise, people used to always, look forward to Schiff or David Hobbs' book or something like that. But this book really brought great relief to the Indian students and readers and the teachers. And it had a very interesting presentation where Professor Ghatak thought of bringing in the historical perspective of the quantum mechanics also. There were Nobel lectures also which were published in that. And I think, sir, congratulations for this achievement. And we are glad that you are blessing us in this particular occasion and hope that you will keep on guiding us in carrying forward the mission of IAPT as well. There is one thing more which I want to say is that we are organizing not only this program, though it is a kind of an inaugural function, but we are also trying that how this can reach out to the people in the country, maybe in the schools also. And the statement of the United Nations, UNESCO's, says that we have to bring awareness about quantum science and technology among common men also. So I think it's a challenge, how we really carry forward this challenge, in what ways, so that people start understanding the nuances of quantum mechanics, which if I quote Niels Bohr once again, he used to say that if somebody says that I understand quantum mechanics, then he is actually making a lie. And I think even today, that is the situation. It is considered something very, very different from whole of physics, and understanding it is, in fact, a challenge itself. But I'm sure that speakers in our programs throughout the year, and I am hoping that we will have 72 lectures available to our audiences. they will be keeping this spirit alive about UNESCO's resolution also. Once again, I welcome you, sir, and we are looking forward to wonderful lectures today. Thank you.
Thank you, Professor Ahluwalia sir, for your words of wisdom and setting the stage for the year-long celebration of IYQ. So now I would move on to introduction of speaker, Professor Ajoy Ghatak. But as you all know, most of us know Professor Ghatak quite well. But I would just briefly give an introduction of Professor Ajoy Ghatak. So Professor Ghatak is currently honorary professor at Optics and Photonics Center at IIT Delhi. During 2021 and 22, he was the president of the National Academy of Sciences India, the oldest science academy in India. He did his MSc from Delhi University and PhD from Cornell University. He is the fellow of Optica, formerly OSA, Optical Society of America, and SPIE. He has authored several books, as Professor Ahluwalia said, his book on quantum mechanics. We have all studied quantum mechanics through his book. And his books include his undergraduate textbook on optics, which has been translated to Chinese and Persian. And in 2025, he has completed his 8th edition of his book on optics. So even at this age of 85 plus, he is very active writing books and giving lectures. He is recipient of several awards that includes 2003 OSA Esther Hoffman Beller Award and the 2008 SPI Educator Award, which was in recognition of his unparalleled global contributions to the field of fiber optics research and his tireless dedication to optics education worldwide. He has also received SS Bhatnagar Award in the year 1979. So here we have one of the most prominent speakers on quantum mechanics, and he has agreed and consented to give a talk on this occasion. So I once again welcome Professor Ajoy Ghatak, and I am eagerly looking forward to once again listening to your illuminating talk. Professor Ajoy Ghatak.
Thank you. Can I share my screen? Screen, document, can you see the slides?
Yes, sir.
Can you see the full slide?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir. Very nice.
Okay, thank you. Thank you so much, Professor Ahluwalia, Professor Vinod Kumar, Professor Putul Desai, Professor Rekha Ghorpade, Professor Joshipura, and all others who are present. And I feel deeply honored for being asked to give the first lecture. And as was mentioned by Professor Ahluwalia, Professor everyone, that the first paper in quantum mechanics came in 1925. That was the famous Heisenberg paper. And Max Born writes that Heisenberg did not know matrices. And so he therefore introduced matrix mechanics, Max Born and Jordan. And then came three of the most brilliant papers by Schrödinger in 1926. And by 1928, the most authoritative book on quantum mechanics came out. That was by P.A.M. Dirac. And this all of you know. And since then, I had the great privilege of learning quantum mechanics from Professor D.S. Kothari, Professor R.C. Majumdar, and Professor Hans Bethe at Cornell University. So it has been a very interesting life for me, and learning quantum mechanics from such great people. And it's indeed a great honor, and I thank Professor Ahluwalia and Professor Putul Desai for inviting me to give this inaugural talk. Right now it is about 6:50, and I prepared about 45-50-minute talk, but I do not want to exceed my time, but whenever you want me to stop, please stop me. So I'll quickly, this is going to be an elementary talk, really, primarily meant for students, but teachers are there. So just to tell them about the basic things, the history and of the evolution of quantum theory. So the 2022 Nobel Prize in Physics has been awarded to Alan Aspe and John Clauser and Anton Zillinger for experiments, just one second, for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. And Nobel laureate Anton Zillinger has written a very beautiful book, Dance of the Photons. And the title of the book is From Einstein to Quantum Teleportation. And this, this slightly on the political side, this he has presented very recently to our Prime Minister Narendra Modi, who met Nobel laureate Anton Zillinger during his visit to Austria in July this year. And he is presenting this book to him. And the social media, our Prime Minister wrote that I had an excellent meeting with Nobel laureate Anton Zillinger. His work in quantum mechanics is path-breaking. I talked about India's efforts like the National Quantum Cache. So it is not only one of the most beautiful subjects, but also politically it is very important to know quantum theory. And I'm glad, very glad that Professor Ahluwalia has mentioned that that he's going to take the quantum concepts to the school level, and that is very necessary. It is at the school level that we must introduce, and not only Niels Bohr said that about understanding of quantum mechanics. Richard Feynman had said that I can say in his famous Feynman lectures. If you go to YouTube and look for Feynman lectures, there's a very beautiful lecture on probability and uncertainty, and in which all students and teachers should listen to that beautiful lecture. And he gave that lecture in 1964 at Cornell University. And he said that I can safely say that no one understands quantum mechanics. But even then, it is one of the most successful theories. Einstein never believed in that. So here is the aim of this elementary talk is to understand basic concepts in quantum mechanics, entanglement, and Bell's inequality. And it was for entanglement and Bell's inequality that the 2022 Nobel Prize was given. The question as to what is light has intrigued mankind ever since he or she could see. Here is a sadhu worshipping the light from the beautiful sun. So we all worship light. Surya Namaskar karte hain. And Isaac Newton had put forward the corpuscular model of light, and he wrote in his famous book on optics that are not the rays of light very small bodies emitted from shining substances, and he derived Snell's laws. Huygens put forward the wave theory of light around the same period at Newton, and he also derived Snell's law. But no one really believed in Huygens because everyone believed in Isaac Newton. And so what is a wave? And as you all know that if you make a string move up and down, you produce every point of the string is moving in the x direction, and you create an x polarized wave. And this is the mathematical description, as this is very elementary, of describing a wave. So if you ask a mathematician what is a wave, he will write down this equation, A cos kz minus omega t as the wave. Why does it represent a wave? Because I can always take the k outside and write down z minus vt, where v is defined to be equal to omega by k. And so at t equal to 0, it is A cos kz, and at slightly later time, the whole curve is shifted by a distance v delta t. So in time delta t, the displacement, the disturbance has shifted, not the displacement. The disturbance has shifted by a distance v delta t in time delta t. So therefore, v, we have just now derived, represent the velocity of the wave, which is defined as omega by k. And k is, of course, 2 pi. You can have a y-polarized wave. If you move the string in the horizontal direction, you have a y-polarized wave. And you can also have a circularly polarized wave. If you rotate the circle, rotate the string on the circumference of a circle, you generate in the clockwise direction a right circularly polarized wave. Similarly, you can generate a left circularly wave. In the case of an electromagnetic wave, it is the electric field at a particular point, the direction of the electric field which rotates on the circumference of the circle. So that is the displacement associated with a light wave. So it was Thomas Young's famous experiment. It is one of the most beautiful experiments in physics. He carried out in 1801. He carried out the double hole, not the double slit, double hole experiment. He allowed almost monochromatic light. He used a Bunsen burner and put a sodium in it, salt in it. So the yellow color came out, and he allowed to pass through a screen having two tiny holes separated by a small distance, and he saw a very beautiful interference pattern. Because if you have a one hole, you get an almost, and if the hole is very narrow, you get an almost uniform intensity. And if you have the other hole, then you get a uniform intensity. And actually, it is the diffraction pattern produced by a small circular aperture. But if both the holes are there, you can say that light plus light can produce darkness. And this is also very beautifully explained in the third volume of Feynman lectures, the double slit experiment or the double hole experiment, and saying that the particle model cannot explain that. So the interference experiment, as you all know, of Thomas Young clearly established the wave nature of light, and the wavelength was calculated by this formula. The experiment is done in these days in higher secondary level. So the interference experiment proved that light was a wave, but how could it propagate through vacuum? This was the question that came up, that if it is a wave, then it requires a medium, and the ether was put forward. Now we know that the ether does not exist. Around the same period of time, the laws of electricity and magnetism were getting developed, and Maxwell summarized those laws. These are beautiful equations that were put down by Maxwell, and these are the equations in free space. That first one is a changing magnetic field produces a changing electric field. The second one is a changing electric field. And this is the concept of the displacement current, which Maxwell had introduced. And he modified Ampere's law to introduce the concept of the displacement current, and he wrote down this equation. Once he wrote down these equations, he could derive the wave equation. And once he derived the wave equation for the electric and magnetic fields, he could predict the existence of electromagnetic waves, and he could calculate the velocity of the electromagnetic. So V was given by under root of 1 over epsilon naught mu naught, and by substituting the values of constants that were available to him at that point of time, it was 1864, he calculated that the velocity of light was about 311 meters per second, velocity of electromagnetic wave. So he predicted the existence of electromagnetic waves, and he said that the velocity of these waves will be about 311 meters per second. And on that prior time, Fizeau had measured the velocity of light, and which was about 318 million meters per second. And he had predicted for the electromagnetic waves to be 311. So these two numbers were almost equal. And with faith in rationality of nature, that these two numbers cannot be accidentally equal, he said that light must be an electromagnetic wave. This is said to be one of the greatest syntheses in the field of science, that the synthesis of the field of optics and the field of electricity and magnetism, that light is an electromagnetic wave. And this is an X-polarized light. You remember I had shown you the string. Here the electric field is oscillating, and the corresponding magnetic, for a plain electromagnetic wave, this is an X-polarized wave where the electric field is oscillating in the X direction, and the corresponding magnetic field, which you can determine by solving the Maxwell's equation, is in the Y direction. So these are the electric and magnetic fields and associated with the X-polarized electromagnetic wave. And as I mentioned just a little earlier, for the right circularly polarized electromagnetic wave, the electric field at a particular point rotates on the circumference of a circle. And this is the displacement associated with a light wave. So then the electromagnetic wave theory was very well established, and people thought that they knew everything of physics. And then 1905 was Einstein's Annus Mirabilis, Year of Miracles, in which in that year he wrote 5 outstanding papers which changed the face of physics. And there's a very beautiful book by John Stachel, the title of which was Einstein's Miraculous Year, Einstein's Annus Mirabilis. That is 1905, 5 papers that changed the face of physics. He introduced the concept of special theory of relativity, Brownian motion, E is equal to mc square. And in the second paper, in his Year of Miracles, Einstein wrote that this is his own words, the English translation of his German paper, that radiation energy, that is light, consists of indivisible quanta of energy, which has the value E is equal to h nu, and its momentum is equal to h nu by c. And he explained photoelectric effect. Many people write that in order to explain photoelectric effect, he developed the photon. That is not true. That is not true. He calculated the entropy of a box containing electromagnetic waves. He compared that with the entropy of classical atoms, and from that he could figure out that light also has a corpuscular nature. It's a very interesting paper, beautiful paper by Einstein that he wrote in 1905. And then using the photon concept of the light quantum, photon came in the year 1926. He derived the Einstein equation, which was verified to a great degree of accuracy by Robert Millikan and confirmed by the experiments of Arthur Compton. So in 1926, Einstein's light quantum came to be known as photon. Now here is an experiment. So here you have Polaroid. I hope you can see this. This is a very crude Polaroid, but I do this experiment with unpolarized light coming out of a laser or a sodium lamp, and you pass through a Polaroid, it polarizes. So here the electric field is oscillating in all possible directions. You pass through a Polaroid and it becomes X. The electric field is oscillating only in the X direction. And this Polaroid has long chain molecules, and the direction of the molecules is at right angles to the x-axis, is along the y-axis. So they absorb the electric field in the y direction and allow only the electric field in the x direction to pass through. If you have another Polaroid which is at an angle, then as you know, the electric field is Ex cos theta, Ex prime is Ex cos theta. So the intensity falls off as cos square theta. This is the famous Malus' law, which we study in our undergraduate classes. So this is the experiment with 2 Polaroids. As you can see, the blue dot is rotating, and this is at 45 degrees. These are very good quality Polaroids, and so half the intensity, cos square 45 is half the intensity passes through. And for 2 perfect Polaroids at right angles to each other, cos square 90 is 0. Please switch off all your microphones, please. So now you use a single photon source, single photon laser that is coming and passing through a Polaroid. And you have, after it passes through, some of the photons get absorbed by that. Let us suppose this is an unpolarized. And then the photon that comes out of here is an X-polarized photon, which I represent by the symbol Ktex. And then if I pass through another Polaroid, then the law of Malus says that the intensity falls off as cos square theta. But my quantum theory says that the probability of passing through is cos square theta. One can never predict whether it will actually pass through or not pass through. One can only tell us the probability, and the probability of its passing through is cos square theta. So I can write down the Ktex, which represents the photon, X-polarized photon, can be written as a superposition of X prime and Y prime for polarized photons. And the amplitude is cos theta here and sin theta here. So there is a probability, quantum mechanics, cos square theta is the probability of finding the photon to be X prime polarized, and sin square theta is the probability of finding it Y polarized. This concept of superposition is extremely important, as I will tell you with some simple experiments. So you have now a linearly polarized beam making an angle of 45 degrees with the IY axis, and you pass through an appropriately oriented calcite quarter wave plate. And as you all know, that after passing through a calcite quarter wave plate, it introduces a phase difference of pi by 2, and you obtain a left circularly polarized layer. But if you now use a single photon source and pass through a polaroid which is 45-degree polarized, then it is a superposition of O polarization. This is the ordinary wave and the extraordinary wave polarization. So it is both ordinary and extraordinary. It's in a superposed state. And it interferes with itself to produce a left circularly polarized photon. It interferes with itself to produce a left circularly polarized photon. Shweta, will you please switch off your mic? Shweta, thank you. So the RCP photon, the right circularly photon, has an intrinsic angular momentum of plus h cross, and the left circularly polarized photon has an intrinsic angular momentum of minus h cross. And an X polarized photon can be considered as a superposition of the right circularly polarized photon and a left circularly polarized photon, just as in classical electromagnetic wave. So thus, if you have an X polarized photon, then you measure the angular momentum of the photon, the intrinsic angular momentum. There is a half probability of getting a right circularly polarized photon and a half probability of measuring minus h cross. Half probability of measuring plus h cross and a half probability of measuring minus h cross. So I must mention, I thought I had the reference. This was first, this concept of the fact that the right circularly light quantum has an intrinsic angular momentum of plus h cross was first put forward by Satyendranath Bose. I have written a small paper in American Journal of Physics to straightening out the history of the development of who discovered the angular momentum of the photon. The Western scientists give credit to Richard Beth in his 1937 paper, but it was actually put forward by Satyendranath Bose. For those who are interested, I will send you the little bit of history that I have written on that. Now, here is a polarization beam splitter. So an unpolarized light beam is such that it splits into two beams. So this is S polarized. In the polarization is in this direction, and part of it is in P polarized. And unpolarized, these are commercially available polarization beam splitters, where about 50% comes here and about 50% goes there, usually abbreviated as PBS, splits in two mutually orthogonally linear polarized beams. Now, if you have a sodium lamp and you make it a 45-degree polarized, then you will say half the intensity comes here and half the intensity is P polarized. Now, on the other hand, if you have a single photon source, now this is very beautiful experiment. If you have a single photon source, you pass through a polaroid, you produce a 45-degree polarized photon, and it is a superposition of S and P. So it is reflected and transmitted. It is here as well as here. But if you put the detectors, as I have indicated, then it is either here or there. So if the detectors are not there, this is very important. Photon is here as well as here, in this beam as well as this beam. But as soon as you put the two detectors, there's a half probability that it will collapse here, half probability of it will collapse there. Where will it collapse? No one can predict. So now you block the transmitted beam or allow the S polarized. The electric vector is perpendicular to the plane of the screen to reflect it to another, and you pass it here. And the detector detects the S polarized. You block this beam and you allow the P polarized beam, and the detector comes here. Then you allow both the beams to be there. And if the adjustments are made, and this is very beautifully discussed in the book by Anton Zillinger, that the 45-degree polarized becomes 45-degree polarized beam, which proves that a single photon, although in principle it cannot be split, you cannot have half a photon, you cannot have half an electron. So it is here as well as here. It is in both beams until you make a measurement. And you can make this interfere with this beam to produce back the 45-degree polarized beam. This is a beautiful experiment. Now let me consider the phenomenon of double refraction. So all of you are familiar with double refraction. You see two images. What happens is, if you have a unpolarized laser beam, this is an actual photograph, double refraction in calcite. When an unpolarized light beam is incident, normally on a calcite crystal, it usually splits up into two linearly polarized beams. So this is one polarization, this is another polarization. One corresponds to the extraordinary wave inside the crystal, and the other corresponds to the ordinary wave inside the crystal. This slide was provided by Professor Lakshmi Narayanan at University of Waterloo. Now, you take a sodium lamp and you pass through a polarize, and you have a 45-degree polarized beam, ordinary sodium lamp that you have in an undergraduate laboratory. You pass through the calcite, appropriately oriented calcite crystal. It splits up into two beams. This is the ordinary beam, this is the extraordinary beam, as you all know. So this is X polarized, this is Y polarized. Half the intensity is detected here, half the intensity is detected here. Now, you replace the sodium lamp. You have the sodium lamp, you replace it by a single photon source. Now, the single photon source is a superposition of the X polarized photon and the Y polarized photon. So you have a 45-degree polarized. So then, will it be here or will it be here? It is in both the beams simultaneously. It is in both the beams simultaneously until you measure it. But when you measure it, it collapses to being either at D1 or at D2. It collapses being either at D1 or at D2. Where will it collapse? No one knows. You can only predict the probabilities. And in this case, the probability is half and half. So you can orient the crystal. So this device is known as an XY device. No matter what the incident polarization is, for this orientation of the calcite crystal, the output beam is X polarized and Y polarized. X is in the vertical direction and Y is perpendicular to the plane of that. So no matter what the incident polarization may be, it splits into X and Y polarization. So it is known as an XY device. If I orient the crystal, then you can have an UV device. So this is my Z axis. This is the direction of propagation of the beam. So this is XY, and then this splits up each polarization into U polarization and V polarization. That is, U polarization means electric field is oscillating in the U direction, and the V polarization means electric field is oscillating in the V polarization. So you can have an XY device, you rotate it, let us suppose this is the calcite crystal, you rotate it, and you have a you have a UV device, you rotate it further, you have a sigma eta device. Now, try to understand this following experiment. You have a calcium atom, and it emits two photons, which are said to be entangled, And that is that if the polarization of one is at right angles to the polarization of the other, that if you pass through this photon through an XY device, and if I measure it X polarized, then the right photon, if I pass through again a XY device, it will be always Y polarized. So now theory tells us that the quantum mechanics tells us that the polarization, these two polarizations are entangled. So therefore, if I make a measurement here, then I don't have to have this measurement. Then I know for sure that this photon coming to the right has collapsed to a state where it is bipolarized. Let me state it carefully. According to quantum theory, the polarization of the photon traveling to the left or to the right is not known before one of them is measured, is not known. If the photon going to the left is passed through an XY device and it is found to be X polarized, then the photon going to the right collapses to a state which its polarization state is Y polarized. These are the famous Alice and Bob experiments. Similarly, if the photon going to the left is passed through an UV device and it is found to be U polarized, then the polarization of the photon going to the right collapses to a state. And these two photons can be millions of kilometers apart. And this collapsing takes place instantaneously. The right collapses to a state in which its polarization state is for sure V polarized. Whatever happened to the one particle would thus immediately affect the other particle, wherever in the universe it may be. Einstein called this as spooky action at a distance. He did not believe this. In 1935, Einstein, Podolsky, and Rosen, this is known as the famous EPR paper, wrote in a paper, and these are their words. Read this carefully. If quantum theory was correct, then two particles, which are millions of kilometers apart, can be entangled in the sense that by determining a property of one of the particles, the property of the second particle can be instantaneously changed. And therefore, some information is going from there, here to there. And special theory of relativity forbids the transmission of any signal faster than the speed of light. This came to be known as the EPR paradox. About 30 years later, experiments confirmed the predictions of quantum mechanics. Namely, Einstein's impossible proposition was in fact correct. Instantaneous changes in widely separate systems did occur. EPR argued, इसको जरा ध्यान से सुनिए. EPR argued that if without in any way disturbing a system, we can predict with certainty, that is with probability equal to unity, the value of a physical quantity, like the polarization state, then the second particle must have possessed the measured property before the measurement was carried out. That means if the left side is X polarized, quantum mechanics tells that the right photon will collapse to a state of Y polarization. Now, EPR said that there is something written on that photon. So I do not know, we do not know, but God knows. But that is not correct. That the second particle must have, so this is the concept of hidden variables. That it is ascribed, it is written on the photon some variable, it is measured property, it must have possessed the measured property before the measurement was carried out. So thus there must, we assume that the photon must carry the information. Thus there must exist hidden variables so that we can assign values of all observables of a system. Now, we are now assuming a hidden variable theory. So one photon is ascribed by variables x, u, sigma. That means if it is passed through an XY device, it will be X polarized. If it is passed through an UV device, it will be U polarized. If it is passed through a sigma eta device, it will be sigma polarized. And the other photon, in the hidden variable scheme, you know for sure that if it is X polarized, then this will be Y polarized because the experiments show that. If it is found to be U polarized, it is V polarized. And if it is right side, if the left side is sigma polarized, then it is eta polarized. So you can have another set. The left is YV sigma, and the right is XU eta. YV sigma means if you pass through a UV device, then it will be V polarized. So the right photon, if you pass through a UV device, it will be U polarized. So this is known. So let there be N1 number of photons which are ascribed these values, N2 this thing, and with 3 setting of the device of the devices, X, Y, UV, and sigma eta, there are 8 possible. You have to sit down and do that. It's very easy. I've done that in my optics book. N1 pairs characterized by these polarization to the left, this polarization to the right. And there are 8 possible, one more. So I want to calculate P of XU. So the left side, if it is passed through an X polarized, it is U polarized. So it is N3 plus N4. So I want to calculate P of XQ. So N3 pairs characterized by this and N4 pair. So the probability of the left photon going to the left, passing through the XY device, measuring X polarization, and the photon going to the right, measuring U polarization, passing through the UV device, is N3 plus N4 by N. Because there are only 8 possibilities. Next, calculate P of X sigma. So X left में होगा, sigma right में. Only these two. So P of X sigma is N2 plus N4 by N. That is probability that the left photon, if it is passed through an XY device, is X polarized. And the right photon is passed through a sigma eta device and is sigma polarized, is N2 plus N4 by N. And then similarly, P of sigma U. So you get these 3. And if I add them up, I get this. And P of XU, I calculated this. So this is greater than this. So you get this inequality. This is a simple form of what is known as Bell's inequality. John Stuart Bell, if he died at the age of 62, that's the greatest tragedy. He was a brilliant theorist and an experimentalist. He used to work in CERN, and in his off time he used to work on theory. And he did beautiful theory and beautiful experiments. Remarkable man. And this is a simple form of, and let us see, if I now use quantum mechanics, what will be P of X comma U? So देखिए, now I am assuming quantum theory and calculating P of XU. So left photon is passing through the XY device and it is X polarized. The quantum mechanics tells, then this will be Y polarized. So I pass through now a UV device and I measure Y polarized. So it will be cos square 90 plus theta. So P of XU is half sine square theta. This is using Malus's law that I had explained. Similarly, you can calculate P of X sigma. And similarly, you have this. So if Bell's inequality is valid, then it will imply that sine square theta must be sine square less than sine square phi plus sine square phi minus theta. And if I assume theta is equal to 2 phi, then this becomes sine square 2 phi. This is sine square phi, 2 sine square phi. For phi equal to pi by 6, This becomes 3 by 4 less than 2 by 4. So this is an impossibility. So therefore, quantum theory and Bell's inequality are not compatible, which implies that either quantum theory is right or theory based on hidden variables, but not both. So there are many experiments that have been carried out. The most beautiful experiment is by Alan Aspect. He considered a calcium source and 2 photons coming out, and you have something like an XY device and sigma U device, and you calculate those probabilities. Alan Aspect writes, इसको ध्यान से पढ़िए, the linear polarization correlation of pairs of photons emitted in a radiative cascade of calcium. Calcium emits 2 photons in quick succession which are entangled, has been measured. The new experimental scheme using 2-channel polarizer is a straightforward transposition of the EPR Gedanken thought experiment. The present results, he therefore calculates those P of XU and P of X sigma and things like that. They are in excellent agreement with quantum mechanical predictions, lead to the greatest violation of Bell's inequalities. So the Bell's inequality is violated. So Bell's theorem, according to Anton Zeilinger, he writes, is one of the most profound discoveries since Copernicus. Bell delivered a death blow to the local realistic picture of the world. Many experiments have demonstrated that the predictions of quantum mechanics for entangled particles are fully correct. And the world is really as crazy as predicted by quantum mechanics. So you can do the same experiment with which we do in MSc, the Stern-Gerlach experiment. So in the Stern-Gerlach experiment, you have silver atoms. The silver atom has the magnetic moment of that of the electron, and the magnetic moment is proportional to the spin angular momentum. So it's split up. It passes through an inhomogeneous magnetic field. It splits up into Z up state and Z down state. Where will it land up? You do not know. If you have a Z up state and you pass through a Stern-Gerlach apparatus in the X direction, then this is a superposition. So it is a half probability of finding here, half probability of finding here. So quantum mechanics is probabilistic in nature. Classical mechanics is deterministic in nature. And if you have something like this, electron, positron, and they split, it's in a singlet state. So if one spin is up, the other is down. If one spin is down, the other is up. So you can carry out, in principle, you can do these entangled measurements using that, but these are very difficult. These are very difficult experiments to do. But in principle, they are entangled. That is, if I pass through a Stern-Gerlach apparatus and measure the spin to be up, then you don't have to measure the second one, it will be spin down. It will collapse. Otherwise, it is in this superposed state, something like that. And this is the photograph of a young lady, which shows that the probabilistic arrival of photons on a photographic plate. This is with 3,000 photons, there are 3,000 spots, and there are 28 million photons. So they are governed by the probability. In the single slit, in the double hole interference pattern, the electron passes through both the holes simultaneously. How does the electron pass through both the holes? One does not know. It is described by a wave function which is present here and here. It interferes with itself to produce a probability distribution, which is the same as the intensity distribution predicted by classical wave theory. I'll repeat. In the double hole experiment, the electron passes through one electron. And how does one electron, which has a definite mass and a definite charge, pass through both the holes? No one knows that. Feynman beautifully writes. No one knows that. So it passes through both the holes. It is described by a wave function which is finite in one hole, finite in another hole, and then as it evolves, it predicts a probability distribution. That probability distribution is the same as predicted by classical wave theory, something like that. So the most fundamental theory now available is probabilistic in form and not deterministic. David Bohm, one of the greatest quantum physicists of our. So I give you below, these are some beautiful textbooks on quantum mechanics. The left side by Dirac, second one is by Feynman, as you all know. The third one is by David Bohm, and the fourth one is by Cohen-Tanuji. All Nobel laureates excepting David Bohm, but many people think that David Bohm should have also got the Nobel Prize. So here is a beautiful photograph of Dirac and Feynman. David Bohm studied so much that he became a disciple of J. Krishnamurti. And my friend Padmanabhan Krishna at Banaras, he knew David Bohm extremely well. And this book was translated by two of my very good friends, Nicole and Dan Ostrowski. What I have done today, I have the wealth inequality derivation I have given in my optics book, as Pruthul mentioned. The 8th edition has just recently come out, and probably this is the last edition. Thanks for your attention. Thank you so much.
So thank you very much, Ghatak sir, for really illuminating presentation on history of quantum mechanics till quantum entanglement. Now, sir, can we take up one or two questions from the audience?
We are already, you see, I started late. I started around 6:50, so it is 7:30. I think we should not, no, I am happy to take questions, but we should not delay the second speaker. Let me have one question, if I can answer.
Okay, if anybody has to ask a question, sir is ready to respond to one of the questions, please.
There is someone called Urvish is raised the hand. So we can ask.
Hello, sir. Am I audible correctly?
Yeah, you can unmute and
Hello, I'm Urvish. Hopefully, I'm audible correctly.
Yes, you
I
are.
would like to. Thank you, sir. So first of all, I would like to thank you all the professor who arranged this, and Professor Khatar for his book of quantum mechanics, which I started to learn about the quantum mechanics. And basically, I'm the master student who is researching in the quantum computing and its application for the physics and finance. So I usually I'm into the developing the algorithms by using the by leveraging the properties of the qubits and all. So I just wanted to ask, like, it was a whatever you explained, it was a total foundation of whatever I'm doing right now. So I just to be direct, we are using the power of qubits to optimizing the algorithms in modern world, like to make a optimize the AI model, optimize the machine learning model in the modern world. So my question is like, uh, how is it like connecting in the modern quantum computing? Like, I don't mean like I'm developing right now, but in some way, some of way, I'm feeling lack of some connection between the foundation of our quantum mechanics and our modern quantum computing itself.
What I would suggest always is that I'm sure Professor Pruthul Desai and Professor Ahluwalia will organize some lectures on quantum computing. I'm not an authority on quantum. I know very little of quantum computing. So what I would request, either if it is not planned for this chapter, some other chapter, to have a session on quantum computing. Quantum communication, as was mentioned in the very first slide, has become as you correctly mentioned, that is become an extremely important subject. So right from beginning to what is the state of the art today, If Putul, if you can organize 1 or 2 lectures of, if you are unable, then the next RC who takes up this, you can have that. Then you can probably answer that. I'm not an authority on quantum. I will not be able to answer that. The algorithms that are used in quantum computing, I have. So let's go to the second talk.
Okay, sir. I take this opportunity to thank Ghatak sir for really an enlightening talk on this history of quantum mechanics, starting from Newton's corpuscular theory of light and reaching up to quantum entanglement, Bell's inequality, and some nice quotation from your presentation. Just I would like to mention before we switch over that Young's experiment, as you mentioned, light plus light produces darkness.
That's Max
Amazing
Born.
thing.
That is Max Born. Sorry,
Okay, so it's amazing, amazing to
Yeah.
yeah, and superposition of single photon and probability interpretation is really wonderful, wonderful way of discussing the thing. So very much thankful to you, sir, for accepting our invitation and delivering an exceptional talk on this. Thank you very much.
Thank you.
Now
Thank
it's
you.
time to switch over to the second speaker of today's
Yes.
event. Let us invite Professor K.N. Joshipura, sir, for his presentation. As Rekhaben mentioned in the beginning, he was also the National General Secretary for 3 years prior to this, and he is also a very well-known figure to physics community, Professor K.N. Joshipura, and he was retired. He was a head of the department from Sardar Patel University, Vallabh Vidyanagar, and he is an excellent speaker, orator. We have numerous occasions to listen to him, and one more is going to be added today. So, without wasting much time of all the audiences, I invite Joshipura sir to take over, please.
Thank you so much. I will first share screen and then start. With this, I am now trying to open my PPT. And I will now. Can you see the blank screen? Hello?
Yes,
Yes,
sir.
yes, yes, sir.
Yes, we
So in the beginning, there is no knowledge, blank screen. Thank you so much. Can you see the logo?
Yes.
Okay, so it means that the things are going on very well. Dear friends, it is a big challenge and an opportunity to speak after Professor Ajoy Ghatak speaks to the audience. It's a joy to listen to Professor Ajoy Ghatak. And with this, this is the curtain raiser, IYQ-2025. I'm going to just having a kind of quantum jumps, various outlines of the whole development. The title is The Great Quantum Theory, and I thought I should add something to the title. So what I have added is Athashri Maha Quantum Katha. In Sanskrit, Atha means the beginning. So I may give you some idea of the beginning, but we cannot have the iti. Iti means the end. It's still going on. So anyway, Atha Shri Maha Quantum Katha. I'll just try to give a flavor of the developments. It will be much simpler. Perhaps the teachers here will be able to get an idea as to how the things can be presented to students. This is about myself. And so I want to now go over to International Year of Quantum Science and Technology 2025, and it has been already mentioned about the purpose, global initiative by the United Nations Organization. I want to thank you, RC-07, and also Professor Ahluwalia for initiating this 3-day program, and also the learned speaker, Professor Ghatak, and a powerful batsman speaker is going to come tomorrow, Professor B. Deshmukh and others. And I should also thank all the viewers. Very nice, friends. We recall the historic period, 1900, 1930. 3 decades that shook physics. Actually, the book by George Gamow is 30 years that shook physics. And the idea is to give some outline of the developments. What began as a quantum theory by Planck and Einstein become quantum mechanics, and that too will be now 100 years old. So the development is quantum theory to quantum mechanics, quantum physics to quantum science. And with applications, it becomes technology and it leads to revolutions. So that is the whole idea behind the IYQ. Very nice. The story began with the black body radiation problem, as everybody knows. You are saying, oh, what is this? Everybody knows about it. Fine, very nice. But my friends, I want to show a small demo video to give you some idea of the black body radiation. It's a demo with the old filament bulb, which is now forgotten, Edison's filament bulb. And it is a good approximation to the black body. So I think I will stop sharing and go to my video. Is it okay? I will stop, right? I will stop sharing here and stop sharing. After this, I can start my video and let us see. I will have to close down this. I'm trying to open this and let me see whether with the share screen, I should, okay, it has started already, sharing. This is about a simple demo experiment. Oh, a lot of, I think, have a look. Don't look at the right hand side. Look at the black dark. You will see something appearing. Can you see this? Note the color and the intensity. Can you see this?
Yes, sir. Yes,
okay.
sir.
Yes, sir.
Gradually,
Yes, sir.
I'm increasing the voltage across the bulb and the intensity of light increases. The color is also changing. Have a look. Don't worry about the right hand side, the graphs. We'll talk about that. Now, the voltage across the bulb is reduced gradually, and see, same thing in the reverse manner. Have a look. Simple demo. This was done by Dr. Tarun Trivedi of Bhavans College, Dakor. Just 1 or 2 minutes more. Now, intensity reduced. Can you see this? Have a look. Now the bulb is fading away like black body at lower temperatures, you can say. Okay. Watch it again. Watch it again carefully. Glowing, glowing. Now color is also changing. You can see. Very nice. I can't see the bulb. Okay. Very nice. So thank you. Very nice. So now I will come back to my PPT. I will need some time to go back to the PPT. Okay. Okay, that was the idea. I'm sharing my screen. Can you see the PPT again, please?
Yes, sir.
Hello?
Yes,
Yes, yes.
And
Yes, sir.
then again, So it began with the black body radiation problem. And I have given you some idea of the black body radiation while an approximate black body in our laboratory is the famous tungsten filament. What do you observe? What do you observe in this demo? There are two things that you observe, two laws of the black body radiation. One is obvious, the amount of light, the intensity of radiation increases with the temperature of that filament, and the other is the color, that is the peak wavelength, let us say, of the black body changes with the temperature. The other graph we could not explain. Actually, in the end of 19th century, they found a particular way in which spectral irradiance from the black body was varying as a function of the wavelengths. Towards the explanation, Planck assumed that the oscillators in the black body, that means those atoms, let us say, atomic oscillators, can emit or absorb only discrete amount of energy. This was an act of compulsion. He said, Planck said, if I assume this, I'll be able to explain the black body radiation curves. So later on, he said this was an act of desperation. And anyhow, in 1900 came the quantum. 1900. Fine. Next, we go to Albert Einstein, who said, why not to concentrate on the radiation or light itself? And so Einstein says, 1905, light or radiation is a shower of energy quanta, packets of energy. Energy of radiation is discrete. Later on, they were called photons. If the frequency of light or radiation is nu, then the energy of each unit, that is energy of the quantum of light, quantum is photon, is h nu. H is Planck constant. So that's how from Planck to Einstein. Okay. Here you say that the radiation is monochromatic. And so where is the monochromatic source of light? Oh, it is handy now. Look at this. This is our green laser torch, and it's an excellent source of monochromatic light. Our common laser torch has a wavelength of 532 nanometers. And I have a question for you. I have a question for the students. How many photons are emitted per second from a 5 milliwatt green laser torch? You can try to find out. Meanwhile, we proceed further. Quantum. Quantum is a buzzword. एक गूंजता शब्द है. Quantum is a buzzword in today's world. Quantum ये, quantum वो, quantum. क्या है? What are the ramifications? What are the words or something like new terms? Well, we have quantum theory, which went on to quantum mechanics. We have quantum jump. We have devices or materials, for example, semiconductors. Semiconductors as such were known, but why is it that silicon or germanium is a semiconductor? What is the structure, solid state structure that causes this property? It came from quantum ideas, quantum principles. We have lasers, and we have QLED TV. QLED is actually quantum dot LED. So there are two things. There are two quantum things in QLED TV. Quantum dot, one kind of a quantum device, and LED, light emitting diode. These are the quanta of things over here. And something more. We now talk of qubits, quantum bits, quantum computing. If not computers, we have quantum computing. And something which I don't know, quantum cryptography, quantum superposition, entanglement, quantum revolutions, first and second, quantum mission, the National Quantum Mission, and of course, IYQ, International Year of Quantum. Going back, friends, the year 2024 marked two centenaries, 100 years. One, Bose-Einstein statistics, and the other, de Broglie hypothesis. Only last month, Up to last month, we had these two. Okay, it tells us that 21st century is the century of centenaries. ये एक शताब्दियों की सदी है. And I want to give you some idea along the timeline of events. But you will say, what you see on the screen is not a line. It looks like an exponential curve. Yes, the developments took place exponentially. Therefore, I have drawn an exponential curve. We can start with 1924 and 25, 26, 100 years back. It happened. So many things happened. 1928, 1929, 30. What was the first thing to have happened? 1924, I said, Bose-Einstein statistics and Bose-Einstein condensation concept. The term boson was coined later on in 1926, but this was one of the two important developments. It was de Broglie who proposed matter waves, waves for even particles. That was in 1924. 1925, now we will celebrate 100 years of the electron spin. People were trying to understand some of the ideas of atomic structure and even the results of spectroscopy. And so on one hand, Wolfgang Pauli, a very unusual physicist by nature, proposed his exclusion principle, Pauli exclusion principle. There should be some restriction in order that we are able to understand the atomic structure. There should be something like a shell structure. And the idea became clear when two young physicists, Uhlenbeck and Gauss-Schmidt, proposed electron spin, an unusual property of the electron. That was in 1925. Then came 1926, a very special year, very important year in the history of physics. 1926, Fermi and Dirac proposed Fermi-Dirac statistics as against Bose-Einstein statistics. In this year, the term photon was coined by a chemist, photon, the quanta of light or radiation. In the same year also, boson was proposed, and so fermion, the other kind of particles, class of particles was proposed. At the same time came the Schrödinger equation, and quantum mechanics was born. Quantum mechanics was born with the Schrödinger equation. There is another Born, which is Max Born, but I am talking about how quantum mechanics was born in 1926. Previously, in the previous year, 1925, matrix mechanics was also proposed. Okay, so to proceed further, we are in the year 1927, and we have the uncertainty principle, Heisenberg's uncertainty principle that comes up in 1927. At the same time, a debate has started. Einstein-Bohr great debate, the Solvay Congress. That was in the year 1928, 1927, now 1928. C.V. Raman discovered Raman effect. Relativistic quantum mechanics was proposed by Dirac, and as a consequence, positron was postulated, 1928. And then we go to 1929. In 1930, Raman got the Nobel Prize, neutrino. So the idea is to tell you, get ready for centenaries, 1924, and then 25 and 26. And so every year, you'll have something to celebrate, the 100 years of important discoveries or theories. Well, that's why we say that it is a century of centenaries. Fine. At the same time, I wish to mention a brilliant chapter in this quantum katha. It's a period 1921 to 1930. This is very important for our country. It was a golden decade in Indian science, and we recall the quantum Indians, the three quantum figures, quantum Indians, Professor C.V. Raman, On one hand, you have Professor Meghnad Saha. On the other hand, S.N. Bose, Satyendranath Bose. Saha proposed the ionization equation, where in a time of almost 1921, when the atomic structure was not known clearly, Meghnad Saha was a colleague. All these three were actually working initially in Kolkata. So Saha, Raman, Bose, we talked about Bose already. Fine. Friends, in physics and in science in general, the discoveries or theories are named after scientists. We have Newton's laws of motion. We have Faraday's law. We have Maxwell equations. We have Doppler effect. We have Einstein's equation. Question is, Indian names are there in scientific discoveries or theories? Yes. You can prepare a list, but I want to quickly outline. Saha ionization equation, 1921, Bose-Einstein statistics, 1924. Bosons were named later on. As I said, Raman effect, 1928. Chandrasekhar limit, almost 1930 or so. Ramanujan, mathematician. Ramanujan passed away in 1920. So, very important year, very important period, 1920 to 1930. As a part of the whole quantum katha, we have these important developments. Just to tell you in outline. A bright flashback, because we are talking about the quantum katha. The place is Dhaka, which is now in Bangladesh. It was in India under the British rule. And the young physics teacher, Satyendranath Bose, S.N. Bose, was teaching Planck's distribution law to his college students. He got an idea. Planck derived his distribution law basically from classical ideas, classical thermodynamics and so on. The only thing he introduced was quantization in the atomic oscillators. Einstein said, oh no, radiation itself is a shower of light quanta. So then Bose was trying to understand whether on the basis of these radiation ideas, on the basis of these ideas, cannot rederive Planck distribution law. So then a distribution, what is statistics or what is distribution law? It is the law of distribution of energy among the number of particles. And what Bose did was to propose a distribution law for identical, indistinguishable particles. And that was Bose-Einstein statistics. Later on, it was followed by Bose-Einstein condensation. There was another young man in those days, 1924. You see Louis de Broglie trying to wonder at something. He says, if radiation has a dual nature, both wave and particle, is it possible? Is it not possible that a particle, the usual particle, electron, could also behave like a wave? It would have wave properties. And we had, in 1925, de Broglie hypothesis, the wave nature of material particles like electrons. These are the developments that took place 1924. Friends, my aim here is to just outline the quantum happenings, just to tell you about the history in the making. And so the details are omitted. You will find quantum jumps in my topics, but that is the purpose. Yeah, exactly. We are now in 2025. 100 years back, things were happening at an amazingly faster pace in the physics world. More questions were raised than answered. And it happens in science or physics. Okay. Dear friends, at this juncture, at this stage, I have a question or a kind of confusion. Should I write or should I not write an equation? Please allow me to write one equation, and that will be in the next slide. 1926, enter quantum mechanics. And here is the pioneering equation. H psi equal to E psi H is the Hamiltonian operator, psi is the wave function. So the system or the particle is represented by a function, wave function, and you have the typical symbolic equation. If you want, you can write it actually in the details. The Schrodinger equation, which we now write, is the gateway to quantum mechanics. Here it is. It is the Schrodinger equation for stationary states, time-independent situation. In the square bracket, you get two terms. The first is the Hamilton. The square bracket is the Hamiltonian. The first term is the kinetic energy operator. It is an operator because there is a derivative operator, Hamilton, the Laplacian operator. So it is an operator. V is also an operator, but V is much better. It is just multiplicative operator. V corresponds to the potential energy of the system. The first term corresponds to kinetic energy operator. It operates on psi, which represents the system, let us say a particle at a particular energy, and in the stationary state is the total energy of the system. This is the Schrodinger equation for stationary states, time-independent situation. Fine. Schrodinger equation cannot be derived. If a teacher is asking, derive the Schrodinger equation, a clever student will say, sir, I cannot derive it. It is not derived from some other equation. Rather, it is established through basic arguments. Let us try to get a flavor of the whole equation, try to understand in a slightly different way, a simpler way. So you can imagine the Schrodinger equation to be like a machine. In a machine, what do you have? You have some input, some processing, churning, processing, and the output. The Schrodinger equation is somewhat like a machine, we can say. And so here is a picture. This picture actually I have derived or I have adopted from our famous book, Halliday-Resnick Crane, extended volume, which I have written, extended volume 4. So imagine a machine where there is an input. In the Schrodinger equation, the input is the potential energy function, V, as we have mentioned. And then the boundary conditions, because it's a differential equation, second order differential equation. So you need two boundary conditions. These are the inputs. Processing means running the machine or solving the equation. In some simple cases, an exact mathematical solution is possible. If that is not possible, we need some ingenious people who can devise approximations. But that is the processing. That is the processing part. Okay. When you solve the Schrodinger equation, what do you get? What is the output of this machine? The output is the solution psi to which probability can be related. And energy eigenvalues. Eigen means specific. Eigenvalues, specific values. Energy eigenvalues, quantum numbers, and so on. These are the outputs. So the Schrodinger equation is like a machine. And for details, for this picture actually, please see Halliday-Resnick and Crane, volume 2 extended, 4th edition. Okay. So this is something like an idea about the Schrodinger equation and about the knowledge that you gain. With this now, I want to proceed further. And I want to ask a question about a huge multi-storied building. Huge multi-storied building which has infinitely many stories or floors. The number of floors is infinity. But it doesn't mean that the height of the building is infinity. What is this? How can it be? I am talking to you about something very special, very standard result of quantum mechanics, and here it is. Here it is. Look at this. What I have described is here the energy levels of hydrogen atom. This is one of those standard exactly solvable problems of quantum mechanics. If you are able to, if you can solve the Schrodinger equation, and it is possible, exact solution of the Schrodinger equation for hydrogen and hydrogen-like atoms is possible. And the result is here. First of all, it gives you discrete energy levels. Secondly, the difference in the level, the energy difference are decreasing. The largest is here from the ground state, 1s, 2s, 2p. These are the notations, S, P, D, F. So in spectroscopy, the alphabet doesn't start with A, B, C, D. It is S, P, D, F because of the notations developed earlier. 1, 2, 3, 4. 4 of what notations. These are the principal quantum numbers. This is the energy. Why negative? Because it is below the zero. It's a bound system. Total energy is negative. And what we have described is the set of energy levels for hydrogen atom. We say that the energy of the electron in the hydrogen atom is quantized. This gives you an idea of energy levels and also transitions. Transitions, of course, are governed by quantum mechanical rules, but we'll not be able to tell you much about this. With this, then, my next slide will tell you two basic aspects. Quantum mechanics rests on two fundamental traits. The wave-particle duality, which is inherent, and uncertainty or probability. There are essentially the microscopic manifestations. You can calculate, try to calculate, for example, the wavelength of a stone, the Broglie wavelength of a stone. You'll find that it is just nothing. Similarly, the uncertainty principle. Perhaps somebody asked a question about uncertainty. Uncertainty, can it be violated, or can we have some experiment where uncertainty principle can be violated? At least I don't know. It's a fact. It's a fact of the micro world. In the macro world, in the day-to-day experience, of course, this kind of uncertainty that we describe in the uncertainty principle is not there, but we have practical kind of uncertainties, but that's a different matter. These are the two foundation stones, foundational aspects of quantum mechanics. Now, suppose that you are asking some questions to quantum mechanics itself. You are asking a question or one or two questions to quantum mechanics. Well, let us ask, dear quantum mechanics, use of ideal problem. These are the ideal problems we study in elementary quantum mechanics, a BSc level or MSc level. What is the use of ideal problems like square well potential or potential barrier or harmonic oscillator? What is the use? They are ideal, exact but ideal. Even hydrogen atom is hydrogen atom. There is a whole periodic table. How do you explain this in quantum mechanics? How do you derive the energy levels and other properties? Let us see what quantum mechanics has to answer. It says quantum mechanics, well, these ideal problems, prototype problems, convey the basic traits of quantum mechanics. It tells you the very nature of quantum mechanics or very nature of systems at the microscopic level. And at the same time, they lead to the development of approximations. My friends, in mathematics, they say every problem, every problem has either a solution or none. If there is a solution, try to find it. If there is none, never mind it. Mathematics. Here in physics, we say, okay, every problem has either a solution, either an exact solution or none. If the exact solution is there, well, find it. If it is not there, try to approximate it. you will get some information. Something is better than nothing. That is the basic philosophy of approximations in quantum mechanics. Okay, with this, another question to quantum mechanics. Why this harmonic oscillator in particular? What is the use of harmonic oscillator problem in quantum mechanics? Okay. The answer given by quantum mechanics is here. Harmonic oscillator problem, the prototype problem is a stepping stone for understanding vibrations of nuclei in molecules or even lattice vibrations in crystals. So it is the simple prototype problem that leads to further development in knowledge. Okay, fine. Now we are asking quantum mechanics. We are converging to the end of this lecture by talk. Quantum mechanics, very fine. Please tell us how we have gone from quantum physics to technologies. That is what we described in the beginning. How do you go from basic quantum physics, quantum mechanics to technologies? We talk about revolutions. How does it all come about? Fine. It tells us basic knowledge about atoms and molecules. Maybe the standard solutions or prototype solutions are only a few, but approximations are powerful. They are supported by computational aspect, computers. And so it is theoretical physics plus computational physics. We get a huge information. We have built up the knowledge on atoms and molecules, not only atoms and molecules, but also crystal structure. Soon after the development of quantum mechanics, a simple model to understand these crystals in terms of quantum mechanics was also developed. They call it Kronig-Penney model. It was developed. And then came the band theory of solids. You see, the point is that the sharp energy levels in an atom or a molecule go over to bands in solids, and depending on the bands, which are a quantum mechanical attribute, depending on the energy bands, the matter is classified into either conductors on one side, insulators on the other side, and semiconductors. And once the semiconductors became known, people went ahead and somebody said, okay, semiconductor as such is a pure material. So let us introduce some innovative idea. The innovative idea was to put some impurity. Impurity means something added that makes it more useful. And then even with this impurities, even with the PN junction diode that we know, somebody got a still more innovative idea. And the idea was to introduce a small material between two junctions. And so it became transistor, 1948. Why am I telling you about transistors? Because when you talk about transistors, you are going from 1926 to almost the middle of the last century, 1948-50. This is almost the first quantum revolution. Transistors. What next? Oh, the next developments were also, next spate of developments also exponential. We had the ICs, the microprocessors, computers, robotics, AI, ANN, for which the Nobel Prize was given, and so on. You started with the Schrodinger equation and arrived at all this. That is the great theoretical development, which led to further developments. Okay, very nice. So friends, now I'm going to the last slide. We have the time constraints, so I thought I would finish well in time, much before time. Have a look at this picture in my last slide. We start with the Schrodinger equation, that is the gateway to quantum knowledge. Either exact solution or approximations can give to can give rise to energy levels for atoms. Even there are energy levels for molecules which are rotational or vibrational, electronic varieties are there. This is the picture that shows the potential energy well for the molecule. And if you look at it carefully, you will find vibrational levels followed by rotational sublevels and so on. The knowledge about atoms and molecules expanded further. We have typically the 1s2, 2s2, 3p, etc., representing the energy levels of the electron in the atom, or here also it can be done. This has given rise to lasers. The idea of laser was first given by Einstein, but it was achieved in practice almost in 1960s. So we have lasers. And then this diagram shows the yet another marvel of quantum mechanics. We are able to classify materials into insulators, semiconductors, and conductors on the basis of the band gap. Band gap is what you have for solids, as I told you. And once the conductors were known, people started working out something else, as I told you. And we had the diodes. What kind of diodes are there? Semiconductor diodes. We have the PN junctions. We have LED. We have the photodiode. We have the photovoltaic cells. Go to your rooftop. If not on your rooftop, there will be somewhere the solar panels. Solar panels transforming solar energy to voltage, that is electrical energy. So these are the developments. And of course, while we talk about this, essentially it was from solids to these developments. All this has led to quantum revolution. One, typically from basic theories to simple devices. And then after 1950, 60, we have new developments, which we now call second quantum revolution. Second quantum revolution is about quantum computers and many things, which we noted down. I don't know about many of these things, very honestly, very frankly. I think I want to stop here without giving further details. So in the beginning, I said this is Atha Shri Maha Quantum Katha. I cannot call it Iti Shri. Atha is beginning, Iti is the end. Quantum Katha has not ended, but we have to end because of the time constraints. So with this, I want to stop here. Thank you so much. If you have any questions, I would be happy to answer. So thank you so much. Very nice of you. I hope I have completed very much in time. I stop sharing. Yes, please.
Thank you, sir.
Oh, yes.
So if we have any questions, then we can take up a few questions. Punit Bhai Suthar. If you have any questions in
There
chat.
is no questions on the YouTube.
Very
right
nice.
No questions
Very
from
nice
the
of you.
YouTube
Questions
channel.
and then comments from our seniors.
So it is open
Or anybody
for
wants to ask
platform.
lively here. Sorry. Punit Bhai.
Open platform right now. There is no questions on the YouTube, sir, right now. Or
Sorry?
in a chat box.
Hello. There is an answer given to the question raised by Joshipura sir.
Haji.
Brijesh Desai David. Brijesh David has answered.
Sorry. Please repeat.
So actually, you had asked that question: how many photons per second are there in a 5 milliwatt?
Already I asked it. So that is the best way. When when you don't expect questions from the audience, the best way is to ask them how many photons are emitted per second from a laser source of 5 milliwatt.
5 milliwatt. Yeah.
Operating at 532 nanometers. 532 nm means 5320 angstrom. So the photon energy is known. You have to calculate h nu. The total power emitted per second, energy per second is known. You can calculate. You can try.
Maulik, please stop. Please stop your audio and video. Maulik, please.
Okay, very nice. All right. So let us go over to some comments from Dr. Ahluwalia and other experts over here.
May I come in?
Oh, please.
Yeah. I think it has been a wonderful start today.
Oh, yeah.
And both the talks were excellent. I think you have set the tone for the year, and I am sure that this will continue. A number of ideas have come up during the talks, and I hope one talk stopped at Quantum Revolution 1, the other went into Quantum Revolution 2. Professor K.N. Joshipura gave us the history of Quantum Revolution 1. And after that, when Bell's theorem comes into picture, that was the beginning of the Quantum Revolution 2 itself. And that was in 60s only. And people had to really, what you call, do something to what Bell was proposing, that how to test whether something which is being proposed is correct or not. So he proposed a kind of an inequality which was put to test by people, which was celebrated in 2022 with a Nobel Prize. I think one can see the importance of quantum mechanics from the fact that Prime Minister Modi went and met Zeilinger in Austria, and the kind of importance, even the governments have to give to this quantum revolution to itself. I think that was what was highlighted by that particular event itself. Maybe it was a good photo opportunity for both Zeilinger as well as Modi, and that was a great, great thing. There are, certain things which have to really do during this particular program, that we have to cover a wide spectrum of areas in which quantum mechanics is making not only waves now, but for the last 100 years it has been doing. When I carry my mobile in my pocket, I always feel that I am carrying what quantum mechanics has done to us, because it is nothing but a marvel of the quantum mechanics itself that it has happened. I think the best part of both the talks was the kind of pedagogy which was used in presenting the ideas itself. I think as physics teachers organization, I think these two talks can be seen as best examples of presenting very tough talks in very simple and engaging manner. So on my personal behalf, I would say that I must thank Professor Ghatak and Professor Joshipura for taking pains to do this. And also, I would like to, commend the way RC-07 came up, and they said, yes, we will be able to do it in the month of January. We will not let this month miss for this program to happen. So I must commend that effort. And I'm sure that now we will be taking this quantum Rath to various RCs to organize this program. The way it has to be conducted has been done. I wish if we can have parallel some programs in the form of quizzes which we can conduct. I would recommend rather this, please pardon me to use this word, to RC-07 that after these talks, if you can really prepare quizzes on the talks which have been delivered and distribute to the community, I think that will be a wonderful idea. So please, I know that there are so many very, very techno-savvy honorable members of IAPT in Gujarat RC, and they will be able to do all these things in a wonderful fashion. So thank you very much, Professor Ghatak and Professor Joshipura. And it is a great start for a great, great year which we are going to celebrate.
Please, please allow me to, Pratul Bhai, please allow me to say something.
Yes, sir.
After the question session was over, there was a question here, and I know the person. He is Parvez Bhai of Palitana. He is a very enthusiastic teacher. He is asking, can the quantum theory supersede, or can the quantum theory become the theory of everything in future? Theory of everything. I don't know. A theory of everything is like lakh dukhon ki ek dawa. Lakh dukhon ki ek dawa, which is still a good kind of imagination. There should be a single theory to account for everything, all forces of nature, everything. What I can say is that currently the issue is to connect quantum theory with gravity. And if that is done, then it would be a step to theory of everything, if I understand correctly. But at the moment, I don't know. At the moment, we are trying to understand quantum theory, quantum mechanics, and its applications. This is all I can say. If there are experts, they can also try to answer the question about this. And so thank you for asking the question. And I don't have the answer.
In my opinion, it is difficult to quantize gravity.
Somebody called Princeton has raised a hand.
Oh, questions after the question now.
Fernandez, Princeton Fernandez.
Good evening, sir.
Oh, yes, please.
So my question is, basically because de Broglie hypothesis says every atom, an atom is basically like half wave and half a wave and half a particle, because it can vary thanks to uncertainty principle. So my question is, if every atom in our body is a wave, then why do we appear solid?
Oh, okay. So our body is a wave, you are saying?
Because every particle is a wave.
Right.
So then our body should also be, partially a wave, as
See, that is the point.
says in the movie.
The key point is Planck's constant h, which is extremely small. So if you try to calculate the wavelength of a moving stone, for example, then lambda equal to h by p. H is very small. P, momentum mass times the speed. That itself is a big quantity. So the wavelength, which we call the de Broglie wavelength, as such, for material objects, macroscopic day-to-day objects, is very small. So a particle in the larger sense, a particle like a stone or a body is a particle. Even if you try to understand its wavelength is so small that it is insignificant. So in our day-to-day objects, please don't worry about the wave nature of the particle. The key point is Planck constant h, which is very small. So that is how the whole idea is that if an electron is moving with some speed, then it has a wavelength which is certainly appreciable, but not the case for large objects. That's the idea. Thank you for asking this question. Don't worry, your body is not a wave, it's a particle. Another dangerous question. Sir, do we have time? Dangerous question has come. According to quantum mechanics, please repeat the question. What is reality? Please repeat I could see flashing. question was splashing over here. According to quantum mechanics,
there is no absolute reality.
Reality is what you see. Reality is what you see. And so there is no reality beyond what you see. Reality is what quantum mechanics says. So it's a debatable question. Yes, indeed. And these are the questions that tell us that quantum mechanics is unfamiliar. And it always presents surprises. If you are not surprised, if you are not confused with quantum mechanics, you have not understood it. This is what Bohr said much earlier. And so my answer is quantum mechanics is what it is. There is nothing like hidden which we don't know. It's all quantum mechanics. Thank you so much. Thank you for asking the question.
So the reality, yes, it is observed reality, means observer.
It's reality. What you see is reality. Right. And somebody is, we don't have time, but somebody was asking in my mobile, somebody was asking about collapse of a wave function. Prathul bhai, can I take 1 minute?
Yes, you can take.
Collapse of a wave function. It cannot be understood in simple terms, but to give an example, think of Ahalya, the Shalya, the stone became Ahalya. भगवान रामचंद्र जी ने एक पत्थर को, एक शिला को छुआ एंड प्रकट होती है अहल्या. Roughly speaking, there are many stones. Bhagwan Ramchandra ji, just to give an example, don't take it literally, just to give an example and then forget it. There are many stones in the way of Ramchandra, Bhagwan Ramchandra's path. Many people have touched the same stone. Ramchandra ji has also touched many stones. But at the instant of touching, at the instant of observation, the system collapses to the state psi. This is collapse of a wave function. If I try to explain this. Thank you. Thank you so much. Okay. Please.
See, so, Viresh bhai?
Yes, sir. So I take this opportunity to thank Joshipura sir for delivering a wonderful talk, Athasri Maha Quantum Katha, starting from that famous statement by George Gamow that 30 years that shook the world of physics, then black body radiation, and then very nicely stated, explained that curve, century of centenaries are coming up for the coming 8 to 10 years. We can have celebrations like this every year to celebrate centenary of some or the other event that has happened in the past. So very nice presentation by both the teachers, both the professors, Ghatak sir and Joshipura sir. We thank you on behalf of IAPT RC-07 for delivering nice talk. We also thank IAPT central body for giving us this opportunity to do a curtain raiser for this IYQ 2025. So we are fortunate enough to initiate this program from our platform RC-07. So thank you all. We also thank the audience, the present listeners who have actually enthusiastically and patiently listened to the presentations by two renowned professors. Thank you all. We also thank Ahluwalia sir, Rekha Gorpade madam, and the other technical experts who have helped to carry out this program in this online mode. Thank you all. Thank you very much.
Before we leave, I would like to announce that tomorrow we will have two more talks, one by Professor Ahluwalia sir and second by Professor PC Deshmukh sir. So tomorrow we'll all meet once again at 6:30 p.m. in the evening for two more interesting and illuminating talk. So on behalf of IAPT RC-07, I will conclude today's session.
Tomorrow's
and
talk,
looking
the link
forward
will
to
be again
tomorrow's
sent.
session and your presence online virtually, and all our wave functions, let it collapse at 6:30 p.m. on this Zoom platform. Thank you once again.
We will get the same link or use
Yeah,
another
same
link.
link. Same link is there
Same
for
link.
tomorrow's
Same.
Okay.
It will be same.
Okay.
Thank you.
Thank you.
Thank you
Okay,
very
very
much.
Bye.
nice.
Thank you. All the
Very
best.
nice.
Thank you.
Best.